Qing Wang, who is a professor and associate chair for research in the meteorology department at the Naval Postgraduate School, so just down the road. She's also an affiliate researcher here at Moss Landing and has been working closely with Moss Landing faculty over the years. So she obtained her bachelor's degree and master's degree in atmospheric physics from Peking University, and her PhD in meteorology from Penn State University, and was a postdoctoral fellow at NCAR before arriving at Naval Postgraduate School. So Dr. Wang has done a lot of work on understanding the interface between the ocean and the atmosphere, so the marine atmospheric boundary layer, and does a lot of field work that combines aircraft and ship and land-based research. So you've probably seen some of the operations that happened last fall and before that at the Shore Lab at the Aquaculture Center. We'll be hearing about some of that type of work today. So let's give a hand to Dr. Wang.
Thank you, Tom. Yeah. Thank you for inviting me. I think last time I was here, it was 2018. So it's only 7 years, So, I think last time I presented about our work on the microwave propagation and how the atmosphere affects that. And today, I'm going to shift the frequency a little bit and to talk about another subject that we have been involved quite intensively. That is on the optical propagation. So we're getting into the visible and the near infrared. And again, being a meteorologist, we're looking into how the atmosphere will affect these EM propagation, this EM signal propagation. All right, I want to acknowledge, people in my group, including Ryan here, Jesus in the back, and then there might be people online, and then also my student Ben Waller and Melissa John Moore, and they are stationed somewhere, So and lots of the work, especially the field work, we've been collaborating a lot with Moss Landing Marine Lab faculty, including now Tom, and also we get help from lots of the graduate students here. And so I really feel excited to come here to actually talk about what you were, on the big picture, what you were doing, So we're all get this checked. All right, so now the topic of my presentation to include introduction to atmospheric boundary layer and Earth's interaction. This is the bread and butter work for my group. So we call ourselves the boundary layer meteorologist. And I will talk about now what are the processes that affects the turbulence and also fog in the close to the surface in the atmospheric boundary layer. And then I will talk about atmospheric scintillation. This is the part that really affects the optical propagation. As a result of small perturbations in temperature in the lower atmosphere. And then I will talk about fog, because everybody is interested in fog. We're no short of fog, and the question is, what can we do to predict fog, and the impact of fog, and that is the visibility. And finally, I will give a summary and conclusion. And knowing that, we don't have a whole lot of meteorologists here, so I want to give some, instead of going into the math and, the meteorology side, so I want to just give like a picture-like thing, so we get the big picture. I think that would be good enough. So atmospheric boundary layer is the lowest part of the atmosphere, normally about 1 kilometer. And the main characteristic of this layer is it's full of turbulence, as you see. Not yet. Oh, okay. Full of turbulence. Okay. And then there is also, this is at the interface with the surface. So at the lowest 10% of this layer, which is lowest 100 meter, and this layer is closely related to the air and sea interaction. And that means we're looking into lots of the exchange of energy and momentum in this layer. And this layer is called the atmospheric surface layer. And this layer can also be fog laden, and we also have cloud, as we all know about the fog and cloud in the summer. Okay? So, and this is these colored little things are the aerosols and gas molecules. Okay? And they actually affect the propagation of the optical signals as well. So, and of course, fog is a major impact on visibility that we always want to know, how we can forecast that better. And on top of the atmosphere, and we always have the so-called capping inversion. This has to do with, this is the subtropical area, and we have the large scale and substance. The air is slowly descending. As it descends, it warms up and dries. So we have this warm and dry inversion on top of the atmospheric boundary layer. So you see the temperature is increasing and the water vapor is decreasing. So that's what we are looking at, the general environment. Now, this is the picture to show the processes at the air-sea interface, okay? And which has very much to do with what's going on in the water and what's going on in the air. And that's where we talk about the air-sea interface. Now, so the main thing we want to talk about here is the sea surface temperature and also the waves, because they really, that's the ocean side and how they affect the atmosphere. And in the atmosphere, we're talking about the wind, and we're talking about air temperature and air moisture. As a result of these combination, and that determines the exchange of momentum, which is directly related to the wind and the waves, and it's also affecting the sensible heat transfer and latent heat transfer through evaporation. And these three quantities are the key parameter that goes into all kinds of meteorological models, and be it forecast model for mesoscale, large scale, climate scale, hurricane, or when we're talking about ocean forecasting. Okay? And either the ocean models, they need to have their own parameterization for specifying these fluxes, or they get directly input, into the model. So these are the key for air-sea interaction at all scales. And at the top of the boundary, this is what I was talking about, the large-scale substance. And also what complicates this layer is the sea sprays, the wave breaking, and this is particularly true in the high wind condition. And it's, for example, in the hurricane conditions, which is largely unknown. And mainly because it's very hard to make measurement, in those conditions. All right, so now comes to fog. Okay, now fog. Some people think about it as a layered cloud coming to the surface. And in some way, it is true. There's one formation of the fog is the lowering of the cloud layer getting to the surface. Okay? Now, however, the result of its being connected right to the surface, it makes a difference, and that makes it different from the cloud itself. And so now here, and we have deposition into the surface, okay? And then the surface wave breaking, and all those large giant aerosols directly go into the cloud if you have the windy condition. And the aerosol and the circulation, or cycle of the aerosol and cloud droplets and itself is a very complicated process. Now, as a result of cloud or fog, and there's radiation involved. So there's long wave radiation and there's short wave radiation. And together with the microphysics, and then some precipitation or drizzle, and that just makes the fog-laden boundary a lot more sophisticated, right? So, so currently, now the forecast models, they indeed treat fog as the cloud, okay? Now, however, and we do know, and they're different. Now, one thing you can think about, which is very interesting, is that, fog layer is normally, it's a stable stratification. That means the temperature in the fog layer is actually warmer than the surface temperature, ocean surface temperature. Now, so that fog layer is also saturated. That means in the fog layer, you have more water vapor than the ocean surface. Normally, we think about the ocean surface as a source of water vapor. Now, in the foggy condition, it could be a sink, because you're losing water vapor to the ocean surface because of these different thermal stratifications. All right, so now, atmospheric effect on optical transmission. And this is getting to the meat of my presentation, okay? And so now, one of those phenomena is what we call the optical turbulence or optical scintillation. And the more familiar term is the shimmering, or winkling of the stars, okay? Now, it's not because of the stars, it's because of the atmosphere in between, the scintillation effect. So you end up with these. So the optical transmission has been studied quite a lot in the field of astronomy, So, in fact, lots of the paper I read was from that, that community. Now, so this gets to near the surface, okay, and then we have even stronger effects because of the level of turbulence. Now, what happens with the turbulence, okay, and particularly with the perturbation in temperature, now you have some beams of light, okay, with this nice Gaussian wavefront, and it moves going through this turbulent layer. And so because of the index of refraction is different, so it's going to go at different speed, changing here and there. And eventually, now this beam the wavefront becomes distorted, or you can think about it as not focused anymore, okay? Now think about if we are doing like directed energy, high energy laser weapon systems. And the reason it can be so powerful because it's focused. Now, if it goes through this lower atmosphere, it becomes defocused, and its effectiveness is largely reduced. So this is one of the reasons we want to study that. And we also have other factors that, other applications which I'll talk about in the next slides. All right, now the quantity, and another thing that we can relate is on a hot summer day, you drive on the highway, and you look in front of you, it's kind of blurred, everything is blurred. That's because when the road is highly heated, you get lots of the perturbation in the temperature, and that's where scintillation happens, everything seems blurred. So that's the scintillation. And the quantity that's associated with scintillation is the so-called structure function parameter for index of refraction. And I'll have one slice of equation to show you what that is. And so here we look into the fog. Okay, it's not just the fog. Aerosol in the atmosphere affects the propagation of visible light. And one obvious thing is the visibility. Now, when we have fog, we have a significant reduction of visibility. Okay, now here, and what we need to be concerned about is visibility itself, and then how it's related to the fog and aerosol size distribution, composition, fog liquid water content, and number concentration. All the parameters that we use to describe the fog. And the question is, which one is the one that we can use? All right, so why do we care about scintillation? Okay, now in addition to the stars, which our group doesn't really care, okay? We're the boundary layer meteorologists. We want to be close to the surface. But, there are like these three things, and free space optical links. This is for optical communication, right? So now we have these networks from the satellite, airplane, and all the way getting down to the household. And so these are in the optical range, and so we need to make sure that the impact of the atmosphere is understood. And this is not only related to optical turbulence, there's also precipitation, fog is all in that. Okay? Now, a second application is what we call the energy beaming. And now that we have lots of the UAVs and USVs going everywhere, in the sky and in the water, and sooner or later they may run out of energy. Okay. Now, how can we effectively transfer energy into these without pulling them out? And this is the newer technology to create the so-called the Internet of Energy, okay? And we use the directed energy, laser beams to transfer energy to these buoys or the UAV systems, okay? And the third application is very much military. Well, all these kind of are related to military operation, but this is more so, that's the directed energy weapon. And this has to do with the visible wavelengths and also the microwave wavelengths. With the visible wavelengths, the amount of power is very strong, and then we can reach the effect of destruction, all right? But you want to be focused, and you want to be focused enough so that it doesn't take a long dwell time, so just a short time, and then you can get to the point, to destroy. Okay? And then there's also the microwave directed energy, and the amount of energy is not as strong as in the visible range, but it serves its purpose for like make it dysfunction. Okay, so not necessarily destroy, but dysfunction, for the objects. So these are the things that that makes us feel. Now this is time we need to understand these optical turbulence more, and particularly now related to the meteorology is how we can forecast these optical turbulence. And so here are some equations of definition. Now index of refraction is very simple. It's just the speed of light, okay, and traveling in the vacuum, which is about 3 times 10 to the 8 meter per second, and divided by the speed of light in a medium. Okay, this medium can be air, can be water, and can be diamond. Okay, and so now normally the speed in the troposphere, the speed of light in the atmosphere is slower than the in a vacuum, but it's very close to that. So when we talk about the speed, and then we just use the same as in a vacuum. However, now when we are looking into the variabilities, okay, and the differences, the spatial variability, and that small change makes a huge difference. And that's what we define the CN square. And the structure function parameter, so we call it, for simple, we call it the CN square. And you can see this is the index of refraction at 2-point lagged correlation, basically. Okay, and then that defines the CN square. And now, we don't directly measure the index of refraction, but we know how to express the index of refraction in terms of temperature and water vapor and pressure. So all the quantities that we actually measure. So the CN square, we can express it in terms of the CT square, which is defined very similarly as the CN square, except it's for temperature. And similarly, we can do it with the CE square, and we can also do it with the cross correlation between water vapor and temperature. So that way, we can calculate the CN square. Okay? Now, this is directly doing the calculation from the time domain. And we can also do the spectra domain. We can do the spectra and look into this spectra where it has the small scale and so-called Kolmogorov spectra. And then from there, the magnitude of that, and we can back out the CT square. That's an alternative way to get CT square or CE square, and eventually CN square. Now, the requirement for this is that we need the high rate data. Okay, not the data that you sample at the weather station, like 1 second, 1 data point. You want to have 1 second, like 20 data points, okay? So 20 hertz sampling, and so that you can resolve the very small scale, centimeters to like a meter scale. And those are the scale of perturbation of concern to optical signal. So we need to resolve that, and people try to do it from forecast model. And we know the forecast model grid resolution, now we're talking about a kilometer. Very high grid resolution, we're talking about 500 meters. So obviously, we cannot directly resolve this, but we have to parameterize that. That means we need to represent these in terms of the forecast quantity, temperature, humidity, pressure, and everything on the grid. And that's what we call the parameterization. So understand these the Cn squared better, and understand the relationship between Cn squared and the other quantities on the grid. And that's the job for us to do the turbulence, so-called turbulence parameterization. So now, in addition to know what is the Cn squared at a given point here, and there are other factors we need to think about. Now here, I want to give an example here. And if, say, I have this beam and going, say, this is the optical link, 10-degree elevation, okay? And this link is a 5-kilometer path, okay? Now, vertically, and it's going through 870 meters if we just do a simple calculation in geometry, okay? Now, so what does that mean? Now, if you look into the measurement of the vertical variation of temperature, this is example from Point Mugu, okay, and in the summer. And the dashed line denotes the top of the boundary, okay? So cooler here and warmer there. And there are situations where we have the Santa Ana wind, and this is where we get very warm above, and the boundary become really shallow. So you can see the range of variability for the boundary going from anywhere of like less than 200 meter to anywhere around 1,000 meter-ish. So 870 meter, in this engagement geometry, and you very much likely go through the entire boundary with the beam. So this means we not only need to understand what's going on near the surface, we also need to know how it varies in the vertically, okay? And most of the variability work people do has been staying close to the surface. And the work my group has been trying to do is to extend that into the upper boundary. So that's what we have been focusing on. Now, another factor is the horizontal variability. Okay, this is the measurement of in the Monterey Bay from one of the past projects. Okay, and this is from the thesis work of one of my students. And now the ocean, you look outside, it looks quiet, like harmless, and seems all homogeneous. Okay, we know it's not harmless for sure. Okay, but and it's not homogeneous, especially in terms of the sea surface temperature. As I mentioned, for air-sea interaction, sea surface temperature is a key quantity. Now here you see, now within the range of about 2 kilometers, and you're looking at a temperature jump, sea surface temperature jump by 2 degrees. And what's the impact of that for turbulence? Now you can just visually see, this is water vapor. Now on the warm water side, you see all these fuzz here, and it's kind of quiet here. Okay, that's the difference with the warm sea surface temperature is going to make. And this is for the wind, and this is for the wind speed and wind direction. It makes a huge difference in terms of the perturbation. And so obviously it makes the same difference for the temperature and optical turbulence. In terms of the 3 fluxes that I talk about, how it affects the sensible heat, latent heat flux, and momentum flux. And you can see on the warm water side, and we have large value, positive, and then it gets to the cold water is even negative for the sensible heat. And water vapor, 100 watts per square meter, and now it almost goes to 0, and this is momentum. So you can see this heterogeneity, okay, inherent heterogeneity over the ocean is something we also need to worry about. Okay, because it changes, if you have a path of 5 kilometers, and it changes, okay, along the path. And so we had lots of measurement. We always look into the sea surface temperature variability, and this amount of variability is nothing special, from our experience. All right, so now, we talk about Cn squared. How large, what's the magnitude of Cn squared for this quantity? Okay, let's be friend with this and look into the measurement and the magnitude of the measurement. This is from the flip, And this is the big buoy, basically. It goes as a long ship, horizontal. When it gets to station, it flips over. And me and Ryan were on it for 30 days, to make this measurement. Well, mainly Ryan and other people, to do all the instrumentation and stuff. And then my PhD student did this calculation for the CN square. And you're looking at different, measurement from different level. First, you notice that the value here is 10 to the minus 15, 10 to the minus 14, and here 10 to the minus 16. So these are really small numbers, okay? And it varies, big time, like 2, 3 orders of magnitude. And here I have a histogram for the measured data. It actually goes from anywhere from 10 to the minus 16 and a half and to 10 to the minus 13 and over the ocean. Okay, so we're looking at close to 4 orders of magnitude change. And then these variability are not random, okay? And so now you can see these low value days have to do with the Santa Ana events, and this high value days, these days have to do with the cold front passing. You have strong wind. So you see here the mean wind is like 12 meters per second, and normally we're looking at below 5 meters per second, okay? And so now, this is a huge range, and it's related to the other parameters, variables of the atmosphere. Okay. Now how, if this has such a large range, do all the range affects optical propagation? And that would be the question. Now, if only the large values is important, and we don't care about those small values. So we did a sensitivity study with a propagation model. Okay. Now, this is the work of Ben Wauer, of my PhD student who graduated already. And so here he was just taking, now I'm taking this CN square value, and then I will run through the model to see if I have engagement of 1 kilometer, what do I get on this side? Okay? And what about 2 kilometer, 5 kilometer, 10 kilometer? So with each CN square value, he will look into this and look into the power on the other side. And then, so he changed the CN square value and do this again. So this figure looks simple, and this is a combination about results from 563 simulations, all right? And then the vertical axis here shows the power you receive on the other end to the ratio to the power at the transmitter, okay? And the horizontal axis is the CN square. And all these different lines are for the different range of engagement, and this is 1 kilometer here, and this is 10 kilometer. So what we see here, now this red line is 90%, and this line is 10%. So here it says it's only reduced by 10%, so we still keep a 90%. And here it says 90% is gone, so basically if this is a weapon system, it's totally not effective at all, and with this. And with these, and and you can see now at the small range earlier in this, and then it changes very small, and then all of a sudden for later on it drops really fast. This is the range where it's super sensitive to the change of CN square, which means if you have any error in your prediction, and then you have big error, in the calculated results for the engagement quality. And we can do a derivative of this per CN square, and you get to the point to know where it's most sensitive. That's these. And to make it easier for application, Ben translated this result into this figure. And so here you can see there's a green region. That means good for deployment. And vertical axis, the CN square. Horizontal is the distance to target. So these are the good performance region, and this is the region where it drops fast. It's very sensitive. This is the point, it's the super sensitive. That's this point here. And this is where it's below 90% depletion, which means it's no good. All right, so now if you look at any single value here, let's say for 10 to the minus 14 of cn squared, that's here. And then you can see now up to 2.1 kilometer, and your performance is still good, right? And then from this on, and to 5.6 kilometer, beyond 5.6 kilometer, no good. And in between, this is where the range is very sensitive and to the variation of the cn squared. And this is where our forecast needs to be very careful about. Okay? And from this figure, you can see now the whole range going from 10 to the minus 16 and all the way to 10 to the minus 12, they're all needed. Okay? It depends on your engagements. Now, the smaller, the larger range, the larger value of cn squared, it affects the shorter dipole engagement distance, and the weaker ones affects the longer distance engagement, which makes sense, right? So now, so no good news for us. We need to get this, accurate for all the ranges, and across 10 to the minus 4th, 10 to the 4th power. All right, so critical to predict cn squared accurately, to understand the nature of cn squared and its variability, identify how it varies with other meteorological and oceanographic variables, and we want to measure that in the meteorology space, temperature, humidity, and everything that we're good about. And we also need to measure it from the optical link. So we look into the effect of the propagation. And that's, in a way, it's a validation. And finally, we need to validate and improve the cn squared model. So what do we do, for this work? And this is an example of what we did over in Barbados from 2023 to 2024. So this is Barbados, and this corner here is our measurement area, and this is enlarged to this. Ryan did this slides, actually. So now we have these red lines, curved lines denote the optical link. So we have, this point, and we are on solid land, but we're going over water. Okay, so and then we can have a tower here, and we can use the scintillometer to have transmitter here and receiver here to measure the optical link, the scintillation. And and then we also have a small boat that's fully instrumented, and it's going from this pass here to measure the meteorological quantity in high rate. And also it has a beacon there so that Ryan has this tracker to track, and then we can measure the cn squared from the optical link. And then we have this aircraft and with this towed platform, and it goes in this whole region, up and down at different levels to measure the in situ measurement. And it also has a beacon on it, and Ryan's tracking and, can receive the signal from there. And then so we make the optical link. And these are all the instruments, for the towers, and then what's on the ship, the meteorological measurement, and beacon is somewhere here. And these are Ryan's optical toys, and these are the imaging that when he tracked the boat, you see the image of the boat. And that's the aircraft. And this aircraft is fully loaded from for all measurements, of meteorology, cloud microphysics, aerosol, turbulence, pressure, temperature, humidity, everything that you can think about. Now, so this is what we did last winter, okay? And some of you were involved in this, okay? And our main site was at the Shore Lab, okay? Now here, our optical link was between the Shore Lab and the aircraft. That's this red line here. And this is, now we have a high-end tracker, and much better than what we had before. And then, so tower, this is 106 feet tall tower, and we have multiple sensors on this. And then by the beach, and we also have this short tower. And the reason being, we want to sample what comes directly from the ocean. And since this tower was 80 feet away from the water line, so the low-level measurement is already contaminated by the land. That's why we need to have this by the fence, the closest to the water line, the possible. And to be even more cautious, and Ryan put this to measure, directly optical turbulence by his tracker, the optical link, so that we know exactly what's happening right at the spot. And in addition to all these, and we also have the radio sound measurement. Some of you were involved in that, okay? And then there's the remote sensing measurement for the wind profile, continuous wind profile measurement, and this is the radiometer, measures the mean temperature and humidity. All right, so looks like I need to go faster. All right, so now these are the measurement module, how the aircraft flies. We have leveled legs, and we also go up and down so that we can get the vertical profiles. And then for the optical link, and then we're fixing it at a given distance, and the airplane would go this way horizontally, and Ryan would track them from the shore lap, to that. And here's the video that you can see, how his mid-wave IR camera to track the airplane, and simultaneously with the visible light camera, so you can see that. And all these images were collected and stored, and then we'll need to do some imaging and analysis to understand, what we actually get. So making the measurement was only the very first step, and there are lots of effort in deciphering the data. And this is why I'm not showing a whole lot of our results from this experiment, because we're still working on it. All right, so now, and I can give some results from previous experiment. And I don't know, some of you may remember the scaffold tower at the shore lab back from, well, maybe you were not here yet, by then. This is from 2021. And we took like about a week to build this tower, the scaffold tower. And in the end, we have multiple sensors here. And then we also have 2 fog monitors here because, as I have always been interested in fog. And here's a nice picture that we took there. And in addition to this, we have the aircraft going this way and all over the place in the bay. And then there are like all these buoys in the water, and we also have the land station at 2 kilometers and 7 kilometers, okay? And this is the result from that, okay, the CN square. And these different lines are from different levels. And so you can see the top level is here, and it's decreasing with height, which is very obvious, okay? Now, if it's over land, this is what we measure. During the day, you have this dome-like, because stronger turbulence, and you have this, and this is very typical of measurement over land. But when we look into the measurement at the shore lab, and you can see the top of the dome was cut off, okay? And when we look into the wind, and we realize this is where we have the westerly wind, and this is when the marine air associated with the sea breeze kick in. So that's the difference between like purely land, and here we are at the coastal land, all right? And, but interestingly, most of our high energy laser weapon system testing all happens at the coastal region, okay? Because, and also all kinds of activity are in the coastal region as well. And this is a better example to show on the individual days, and you can see this is the 3 level, top level, medium, middle level, the bottom level. So you can see this is the color is the wind direction. Now when it's greenish is from the west, that's when the sea breeze come in. So you can see, the sunrise, and then the sea breeze kicking, it drops off, and then the next day it drops off. So sea breeze have the significant impact at all levels as we observe, from this tower measurement. Now this one, we can combine the aircraft measurement and the tower measurement at the shore lab, 2 kilometers, 7 kilometers. See, this is the dome-like thing that I mentioned earlier, and then this is from the shore lab, and it comes down when the sea breeze kick in. And to look into the spatial variability, we can look every 5 kilometers, and then at the shore lab, 2 kilometers, 7 kilometers. And this is what we see. Now over the ocean, and it's like there are variability, but magnitudes in general small. At the coast, at the shore lap, it's larger, and then when you get to the inland, it's a lot larger. If we zoom into this part here, so we can see all these low value better, and you can see the variability in the over the ocean. We're looking at at least 3-4 times difference, across this region. So spatial variability and horizontal variability is all there. And this is the aircraft going through, the up and down, so we can look into the vertical variability. And these are the 4 cases. And so for 4 cases, these are convective boundary, these are the stable boundary, and these are temperature, humidity, wind speed, and turbulent kinetic energy, and this is the CN square. And what you see for the CN square is, near the surface you have large value, and it decreases as you go up to like the upper 1/3 of the boundary, and in the inversion it starts to increase. And we see this in the other case as well, not so much for the variation below, but it's obviously, we have an increase in the inversion. Now, in the stable boundary, it's a different story, because there's no strong inversion. So there's still lots of variability and not too much difference, at the top of the boundary. And the interesting thing is turbulence is a lot weaker in the stable boundary compared to the convective boundary, but CN square is not necessarily small. And that's the thing with the CN square. It's related to turbulence, but it's not directly related to the dynamic turbulence. After all, it's the perturbation of the temperature, which is a scalar. All right, so much for the optical turbulence part. I'll go quickly into the fog and visibility. So forecasting fog involves, we need to do 2 parts right. Now, one part is we need to forecast the fog, micro fog variables correctly. That include the fog liquid water content, number concentration, droplet size, and all those characteristics of the physical character of the fog. Now, if we get that right, there's a second step, how we can relate these quantity to visibility. Okay? And I want to show this part of the relating to visibility. Now, this is from our measurement and in some previous, like a formulation, like a parameterization, relating fog liquid water to the MOR is a meteorological optical range, which is visibility. Okay? And now, so you can see lots of scatter. That's the first thing you see as a function of liquid water content. This is as a function of the total number of concentration, and also you see lots of the scatter. Now, if you pick, one value of the liquid water content at this value, now the range of variability for the visibility is from 260 to 1,000 meters, and that's a huge variability. And if you pick any number here, and the range is from 360 to 2480. So that's also a large variability. Now, what caused this variability? That's the first question. Maybe it's natural variability, okay? And maybe, now, the visibility is not a unique function of QL or ND, maybe it's a combination of both, or maybe there's something else that needs to go into the picture so that we can help reduce this variability. And so there are efforts, trying to work on that. And this guy, okay, was his paper of 2020, and he used this so-called fog index. It seems like it's at least is putting things together, one on top of each other, but it doesn't really reduce the variability. And we're still looking at, like 420 to 1,400 meters. So that's still a problem that we need to figure out. And the other thing we want to know is how much vertical variability we see, okay? Because when you look into all fog research, they just say we set this up and we did the measurement, okay? But they don't really talk about exactly what level. And it's a natural question, how much vertical variation there is. So to answer that question, I was just curious to see how much. And then we put these fog meter at 2 levels, 5 meter and 10 meter. And so green is the 10 meter, and orange is the 5 meter. So you do see in the liquid water content there is a difference. Now here you can see liquid water content and 10 meter is much larger compared to the 5 meter in general. This is another case, same thing. And it's because the total number concentration is a lot larger compared to the lower level. And the droplet size seems to be pretty much the same, except for this period. Okay, that's look like a special period. But in general, it's the number concentration change with height. Now, this is only 5 meter difference, and we're looking at a significant difference. So this got us interested, and we figure we need to do better to look into the vertical variability. And then so we designed this, we call the crane-based cloud aerosol measurement system, CCAMS. Okay, and this basically a big box with all kinds of stuff that we can put in there to measure turbulence and fog microphysics, aerosol, sea surface temperature, whatever we can think about, because we're using the crane. We're not afraid of the weight, okay? And also we did some research, and we found out on the side of the ship, the disturbance, from the ship body itself is actually minimum. So that gives us an idea. And with the crane, we can lower this and raise this higher and lower this, so we can look into the vertical variability. Since we already know between 5 and 10 meter, there is a measurable difference, and we can safely just go, and look into the difference. And that's what we did. Okay, this is from the Grand Banks, offshore of Nova Scotia. This is in the experiment from 2022. So we had the CCAMS. It's going at each level is about 10 to 15 minutes. All right, and so that's the altitude. And then we look into the the mean of all these. Okay, so this is liquid water content, droplet size, the temperature, and what we identify are significant variation with number concentration. And with, you see these are the variance, so it has good significance, okay, and because they don't overlap a whole lot. And then you see the visibility, how it drops fast as you go up. And this is the difference between lower, the 10 meter, and this is on the top deck at about 27 meter, all right? And then, so we do see this similar to what we observe here at the Shore Lab. And we look into the spectra, which really interesting. Now, first of all, you see these, you have a peak at the lower size, and then you have a peak at the larger size. So we see this consistent or persistent bimodal distribution for the droplet size. And this is what we observed here on the West Coast, and also in other areas in the fog, but not necessarily in cloud. So obviously, there's something going on in fog. And we also identify now this lower peak, it varies with height quite consistently, which also makes us curious what's going on. So we are now working with the modelers to try to understand, the physics of all these variability. Now, in terms of the visibility, and we use these data to plot, the same as I did before with lots of scattering. So this is liquid water content, the visibility. Now, not too clean for the for liquid water content relationship, but it's super clean when we look into the number concentration, which is very interesting. Okay, now that we're just doing different levels. Okay, now we have these large variation in visibility and number concentration, but we don't have the other variations like synoptics or whatever, aerosol difference. This is all in the same environment. So you can see when we clean up all the other factors, it's a pretty nice relationship with exponential relationship with the number concentration. So this gives us some direction of focus now what we should do. And last year, not last year, 2 years ago, this is 2023, we did this again over the Yellow Sea, and this is the picture of that. You can see now we get more experience, and we deployed lots of them at 3 levels, in 1 day. And Ryan processed this data. I don't want to go into the detail, but you can see here, this is number concentration. In general, you see this increase, over this is the fog over the Yellow Sea. And so, we are looking at about every meter, you're looking at a change of 12 number per cubic centimeter for every meter. So, we also see in general the decrease in visibility. And we are still trying to understand this measurement. So now this comes to my conclusion here. So optical scintillation by the atmospheric temperature perturbations and scattering and by the fog droplets are 2 major phenomena. And in the lower atmosphere affecting optical signal propagation. And recent research and focus on the quantifying atmospheric variability of the CN square, and our advantage is to use multiple platforms, so at sea and over in the air and on land, so that we can get a consensus of the different data. And we found out, it's related to the corresponding variability, wind speed, air sea temperature difference, and of course, if it's the land surface, ocean surface, or the coastal region, that makes the difference. And we persistently see the CN square decrease with height, so near the surface, we have large value. But then when you go into the inversion here on the west coast, and we see this enhancement in the inversion. Now, when we went to Barbados to do the aircraft, those are mostly cumulus cloud. Okay? We don't have a strong inversion and a dry layer above. We don't see that. We don't see this enhancement. So, so that structure of the enhancement, it has to do with where you are, what kind of a synoptic system you are looking at. And then coming to the fog here, droplet size is a bimodal distribution, okay? And total number concentration of fog and seems to decrease. And then visibility, increase and visibility decrease. That's the consistent signature that we have observed in fog. And then, with the sea camps where we have only just the fog and visibility as parameter, variables, everything else is fixed, and then we start to see a very clean relationship. And that's pretty much I want to talk about. And finally, and most importantly, I want to thank Moss Landing. And so you have been a huge support for me in the past 10 years. So I want to specifically thank on the science team, Tom here, and late Kenneth Cole, who we started the relationship, John Doc JD at the small boat operation, Basil, who is now working with me still, and all the student helpers, and over the years for radio sound launches, for setting up instruments, for everything you do. It meant a lot to me and to my group. And also want to thank Pedra, for her support, and Ivano, and as the interim director, and Jim Harvey, and that's where I started this. Kathleen Donahill did lots of the paperwork for us to get the approval process done, and then Matt and also Garen, for also approval side, and of course the San Jose State University Research Foundation has been managing my funding, doing all the purchasing and everything for us, and thank you, everything, and thank you for coming to this presentation.
Thank you so much. I have a question. I don't know too much about meteorology, so I'm not sure if this is a basic one, but just thinking about the number concentration of fog droplets increasing with height, how would one anticipate that to continue if you could sample higher up into that atmospheric boundary layer?
Well, that's my question too.
Hypotheses?
So the problem is we can't go, we can't use an aircraft, so, and then we are kind of limited to the height and we can go. And this is why I'm working with some modelers doing the large eddy simulation model. And they seem to show it continues to increase, so, we've been talking about it, so in the marine environment, it's basically, and it's just, very close to saturation anyways, right? And then, so any perturbation for these droplets to cycle in the air, and the droplets just keep growing. So at first we thought, the second mode, it has to do with collision and coalescence, and but the model tells us no, it's the condensation, So and then these, the stronger the turbulence, and then it goes through the entire layer. Particularly in the fog, it can generate turbulence on its own because of the radiation cooling at the top, So it emits infrared radiation to the air. But the air doesn't have a strong emissivity, so it doesn't radiate back the same. And plus, the air above is cool, in temperature. So at the top of the fog layer, and you have this net radiation loss, you generate cooling bubbles, so that generates turbulence. And this is the same way as you have turbulence in the stratocumulus cloud. Like when you fly into Monterey, the airplane, get into the cloud, all of a sudden you start to feel this, okay? Those are generated by infrared radiant cooling, and that's, the same in the fog. So, so we would expect, it's going to continue to change, but we need observations. Maybe we should do some UAVs, that we don't care about losing. To do it. So, that's a very good question.
It's a great talk. Thank you very much.
Thank you.
So I was curious about with the heat transfer inside the fog. I believe you mentioned something at the beginning of the talk about the fog being warmer than the sea surface.
Yes.
As well. So my study species spends a lot of time basking on the surface. And I was wondering, so if I'm a big fish, a shark, sitting on the surface of the water in fog, am I going to be warming up compared to if I was down further in the water column? Is there a heat transfer from the fog into objects on the surface of the water?
Well, it's hard to say, because if you think about the latent heat, right? So if you have water vapor condensing, into the ocean surface, and that's, like evaporation is cooling and condensing is warming. So it's going to warm up the surface. Now, and then you have the temperature, and it's warming, warmer, and then the direction for the heat transfer is also going to the surface. But then I want to say the magnitude of these are pretty small. So I don't know if it's strong enough to warm up the ocean surface that even the whale can tell, So our instruments sometimes cannot tell, because our measurement capability, with all the variability of turbulence, we can only sample 10% accurate at best. So maybe it's that 10%, I don't know, whale may be more sensitive, sometimes animals do. So yeah, that's a very interesting question. I never thought about it.
Thank you.
I have a question. So for modeling CN squared, is the main challenge getting the temperature variance associated with turbulence correct, or are there other factors that the modelers need, like aerosols?
Not the aerosols, but mainly the turbulence. Actually, in my abstract, I had I had planned to talk about the modeling side. We did develop a column model, a second order turbulence closure model to do the simulation. So CN squared doesn't go into the aerosol doesn't go into that. But it's more like how you can relate the variation of the turbulence, to the CN square. Now, there are theories to relate the variance to the dissipation rate and then to the CN square. And like in my model, and also what's currently implemented into COAMs, the Navy's forecast model, and that use that idea. Now, there are lots of other applications, and because they don't have the variance, okay, you need the high rate perturbation to get the variance. And in the turbulence model, you need the high order turbulence closure model to get the variance. So, and what people have is the mean temperature. So they try to use this parameterization called the Tartarsky parameterization to use the mean gradient, and then there's the length scale, turbulent length scale associated with it, and that turbulent length scale is the most unknown. So people just make guesses. So it's at best it's a parameterization. So so there, that's the actual difficulty, and people are having.
Any other questions in person or online?
Any
Okay,
questions
thank-
online?
oh, we do have one more.
All right, thanks for your talk. When I was listening to your talk and thinking about optical distances through the atmosphere, I was thinking about all of the oceanographic observations we make from satellite. And I'm sure that the Navy is probably interested in optical transmission to satellite. And you mentioned that a lot of these processes are not well resolved in the atmospheric models. And I'm curious to the extent that the unresolved or unparameterized processes may be influencing signals that are received at the satellite, and what errors that might cause in us interpreting things like chlorophyll or other things that we measure from satellite.
I think that's possible, and but it also has to do with what wavelengths we are talking about. So for your ocean remote sensing, you probably have some specific wavelengths, and and also it has to do with what you are sampling actually. So I'm not too sure. I think what wavelengths are you talking about? Are you thinking about?
Well, I guess for chlorophyll, it's green blue, like 555 for
In the visible.
Yeah.
I see. Yeah. Well, the optical scintillation does affect that. I'm not sure, so if people should look into that. Because these are the very small scale thing. And if what they're sampling is like a larger variability, larger scale variability, and it's probably, that scintillation effect is a moot point. It doesn't really make an impact on the measurement. That's just my gut feeling, so, but very interesting question, so, yeah.
I think that's it, so thank you very much.
Okay, thank you for coming.